Hello again, aspiring DevOps engineers. If you haven't had the chance to watch episode 1 of our comprehensive interview prep series, make sure you check it out in the description below. Trust me, it's a foundation you wouldn't want to miss. And to all our dedicated viewers, welcome back. In this episode, we're going to dive deeper into our interview preparation process. So grab a notepad, stay focused, and get ready to level up your DevOps interview game. Studying for technical interviews will sometimes feel overwhelming, but I promise you, every bit of effort you put in will pay off. So here's the deal. Watch this video to the end. We're going to cover more ground, share more insights, and equip you with strategies that can make all the difference. Remember, we're in this together, and by the time you're done, you'll feel more confident and prepared than ever before. Before we dive into today's interview preparation process, a quick reminder, you can mix and match the tips and tricks we've shared across all of our interview prep episodes. Think of it as building your own interview toolkit. The more versatile it is, the better you are to tackle any challenge that comes your way. Now, let's leverage the knowledge we've gained in the previous episodes and apply it to the second interview preparation process. You ready? Let's get started. For this specific episode, we'll switch things up a little bit. While Glassdoor served us well last time, this round, we're heading over to LinkedIn to find a perfect job posting that aligns with the DevOps aspiration. Remember, it's not about random questions. It's about tailoring our preparation to the specific requirements of the job. As usual, I'm drawn to the senior DevOps engineering roles, not only because I'm confident in my skill set, but to be honest, the allure of a better compensation doesn't hurt as well. Money, money, money. Anyways, let's take a look at this one. I believe this job posting aligns perfectly with what we're seeking. They're looking for someone well-versed and iterate on the technologies, tools, and best practices you employ to achieve this goal. If asked that question, I'll say, absolutely. If I was tasked to deploy a highly scalable web application that must maintain uptime during the deployment process, my approach would be to prioritize a combination of strategies to ensure a seamless scalability, minimal disruption, and sustain high availability for the users. To begin, I would employ a blue-green deployment strategy. This involves maintaining two identical environments, one handling the live traffic, which is the blue environment, and the other handling deployment updates, which is the green environment. By keeping these environments in sync, I can instantly revert to the previous version if any issue arises during the updates, thereby minimizing downtime. To manage traffic distribution, a crucial element will be implementing a load balancer at the front end. Cloud-native load balancers or services like the AWS ELB can evenly distribute incoming traffic across instances, optimizing performance and preventing any prolonged disruptions. For scaling, I'll make use of the auto-scaling groups to dynamically adjust the number of instances based on the traffic patterns. Leveraging cloud provider features like the AWS auto-scaling capabilities will allow the application to efficiently handle the different loads and ensure continuous availability. To mitigate disruption, comprehensive health checks and pre-deployment testing will be performed on the green environment before rolling out any updates. This approach guarantees that only healthy instances receive live traffic, minimizing the risk of any issues affecting the user. In terms of technologies, I'll focus on implementing infrastructure as a code using tools like Terraform to ensure consistent and repeatable infrastructure provisioning. Containerization through Docker will maintain a uniformity across the develop, test, and production environment. Kubernetes orchestration capabilities will enable efficient management of the containerized application, while Kubernetes built-in service discovery mechanism will help maintain access to the application during updates and scaling events. Utilizing services and load balancers, Kubernetes dynamically routes traffic to the available instances, ensuring users can interact with the application seamlessly. The rolling update strategy with Kubernetes will facilitate a gradual replacement of instances, minimizing downtime while updating the application. Continuous monitoring through Prometheus and Grafana will be in place to track performance metrics, resource utilization, and traffic patterns. Automated alerts triggered by abnormalities will be sent out for rapid response and interventions. Finally, post-deployment validations will involve meticulous testing and verification to ensure that the updated application functions as intended. This includes automated testing, load testing, and end-to-end validation, ensuring a smooth transition for users. In conclusion, my deployment strategy will revolve around a well-structured combination of blue-green deployment, load balancing, auto-scaling, pre-deployment testing, and continuous monitoring, employing Kubernetes for orchestration, infrastructure as a code for consistent infrastructure provisioning, and containerization for uniformity. This will collectively contribute to a seamless, scalable, and highly available deployment process, aligning with the demand of any modern DevOps engineering role today. Question number 2. Can you elaborate on your hands-on involvement with container orchestration platforms aside from Kubernetes? Contrast these platforms with Kubernetes, focusing on their distinct features, advantages, and challenges. Additionally, dive into advanced Kubernetes concepts like node tainting and your application of these techniques. Elaborate on your familiarity with service discovery mechanisms within Kubernetes, elucidating your preferred deployment strategy in your current Kubernetes setup. If asked that question, I'll say, certainly. My hands-on experience with container orchestration platforms extend beyond Kubernetes, encompassing platforms like Docker Swarm and Apache Mesos. While these platforms offer certain advantages, Kubernetes stands out for its robust feature set, vibrant community, and wide adoption. Docker Swarm is known for its simplicity and ease to use. It integrates seamlessly with Docker, making it a suitable choice for smaller applications or teams looking for a quick setup. However, compared to Kubernetes, Docker Swarm's ecosystem may have limitations in terms of scalability and advanced features. Apache Mesos excels in handling diverse workloads and offers excellent resource optimization. Its architecture enables fine-grained control over resources, making it suitable for large-scale applications with varying resource demands. However, the learning curve for Mesos can be steeper, and its complexity might be a lot for smaller deployments. When comparing these platforms to Kubernetes, Kubernetes shines due to its extensive feature set, including automated scaling, self-healing, and rich networking capabilities. The Kubernetes community is vibrant, leading to rapid deployment and continuous improvement. However, Kubernetes complexity might require more time to set up and manage initially. Regarding advanced Kubernetes concepts, I'm well versed in node tainting. Node tainting involves labeling nodes with specific attributes to influence pod placement. By tainting nodes, I can control which pod can be scheduled on them. This technique is useful for scenarios where certain nodes have specialized hardware or security requirements, ensuring only the appropriate pods are deployed on them. In terms of service discovery within Kubernetes, I'm proficient in leveraging Kubernetes native services and ingress resources. Services abstract the network, allowing pods to discover and communicate with each other using DNS. Ingress resources provide external access to services and handles load balancing and routing. My preferred deployment strategy involves creating a service resource to expose the pods within the cluster and an ingress resource to manage external access. This approach enhances scalability and simplifies update. I know you spoke about wanting to migrate from EC2 to AKS. My experience aligns well with this migration goal. I'm equipped to lead the initiative by designing migration strategies, orchestrating the transition, and ensuring a seamless shift while maintaining application availability and performance. My familiarity with Kubernetes deployment, scaling techniques, service discovery, and its advanced concepts positions me well and effectively to manage the pivotal responsibility upon joining the team. Question number 3. Within a cloud-native ecosystem, how do you guarantee the security of your containerized applications? Provide me with a concise overview of your primary security measures and mechanisms that you implement, covering aspects ranging from safeguarding the application code to fortifying infrastructure security and managing identity and access. If asked that question, I'll say, within a cloud-native ecosystem, ensuring the security of your containerized application is paramount. To achieve this, I'll implement a comprehensive set of security measures and mechanisms, starting with application code security. I would enforce best practices such as using trusted base images, scanning images for vulnerabilities, and regularly updating dependencies to mitigate potential threats. Utilizing code signing and implementing image signing policies will further enhance code integrity. Infrastructure security will be fortified through measures like network segmentation, where container clusters are isolated from public networks. I'll also implement network policies to regulate communication between the containers, and I'll use firewalls to control inbound and outbound traffic as well. For identity and access management, I'll employ the principle of least privilege by granting only the necessary permissions to the container. Role-based access control will be implemented to control who can access and modify the resources. Utilizing Kubernetes native authentication mechanism or integrating it with identity providers like LDAP will enhance authentication and authorization. Securing communication between the services within the cluster will involve enforcing TLS encryptions for inter-service communication. I'll also configure pod security policies to define security constraints, ensuring that the pod adheres to predefined security standards. Intrusion detection and prevention systems will be utilized to monitor and respond to abnormal behaviors. Regular audits and vulnerability assessments will be conducted to identify and address potential risks. Logging and monitoring using tools like Prometheus and Grafana will provide real-time insights into the system's behavior, aiding in identifying and mitigating threats. In summary, a robust security strategy within a cloud-native ecosystem involves safeguarding the application code, fortifying infrastructure security, and managing identity and access management effectively. By combining these measures and mechanisms, I would establish a secure foundation for containerized applications, mitigating risk and ensuring the integrity and availability of the overall system. Question number 4. Discuss the advantages and disadvantages of using infrastructure as a code for managing cloud resources. Provide examples of infrastructure as a code tools that you're familiar with and how it contributes to automation and scalability. If asked that question, I'll say, that's a nice one. Embracing infrastructure as a code for managing cloud resources presents a range of both advantages and disadvantages that can significantly impact the way cloud infrastructure is handled. On the advantageous side, infrastructure as a code introduces a level of automation and consistency that is instrumental in modern cloud management. By defining infrastructure through code, I can automate the deployment and configuration of resources, which not only reduces the chances of human error, but also ensures that environments are set up exactly as intended every time. This aspect of automation significantly enhances efficiency and reliability. Moreover, infrastructure as a code brings the benefit of version control into the realm of infrastructure management. As I work with tools like Git or an S3 bucket, I can maintain a history of changes to my infrastructure, enabling me to track the modifications, collaborate more effectively with the teams, and implement well-documented and revisable changes. Scalability is another notable advantage. Through infrastructure as a code, I can swiftly adjust the scale of the resources to accommodate the changes in demand. By modifying the code, I can easily replicate or adjust resources, making it seamless to manage resource capacity and optimize performance. However, it's important to acknowledge the disadvantages of infrastructure as a code as well. Despite its efficiency, the learning curve associated with understanding and writing infrastructure as a code can be steep, especially for those less familiar with coding practices. Additionally, complexities can arise when dealing with large and intricate infrastructure configurations, potentially leading to code-based complexities and maintenance challenges. In terms of tools, I'm well versed in using tools like Terraform, AWS CloudFormation, Ansible, Chef and Puppet, and more. These tools provide a domain-specific language to define infrastructure as a code, allowing me to create, manage, and version infrastructure resources. Their declarative approach empowers me to focus on the desired outcome rather than the specific steps, contributing in enhancing efficiency and reproducibility. In conclusion, while infrastructure as a code undoubtedly offers numerous advantages in terms of automation, consistency, version control, and scalability, it's important to weigh this against the learning curve and complexities that might arise. My experience with infrastructure as a code tools like Terraform and AWS CloudFormation equips me to harness these advantages while navigating the associated challenges to effectively manage your cloud resources. Question number 5. Imagine you're tasked to optimize the performance of a database-intensive application running in a Kubernetes cluster. What strategies and tools would you employ to achieve the optimal database performance and scalability? If asked that question, I'll say, if faced with the task of optimizing the performance of a database-intensive application within the Kubernetes cluster, I'll implement a strategic approach encompassing several key steps and tools. First and foremost, I'll focus on the database optimization at the application level. This involves analyzing query performances, identifying potential bottlenecks or inefficient queries. Profiling tools like the MySQL Performance Schema or the PostgreSQL PG State Statement will provide valuable insight into the query execution time and resource consumption. To enhance database performance and scalability, I'll leverage a caching mechanism. Utilizing an in-memory cache such as Redis could significantly reduce database load by storing frequently accessed data. This approach accelerates the data retrieval process, minimizing the need of repeated database queries as well. In terms of Kubernetes-specific strategies, I'll consider optimizing pod resource allocation, ensuring that the pod has the appropriate CPU and memory limits, and also requests can prevent resource contention and enhance overall stability. Horizontal database scaling could be explored by sharing data across multiple database instances or replicas. Kubernetes stateful set could facilitate managing stateful applications like databases, allowing for the control, scaling, and reliability of our databases. Furthermore, I'll consider implementing read replicas to offload the read-intensive operations from our primary database instances. This can particularly be effective in distributing the load and enhancing the read performance. Monitoring tools like Prometheus and Grafana will play a crucial role in maintaining database health and identifying performance issues. Custom metrics and alerts could be set up to trigger notifications based on predefined thresholds. Lastly, I'll periodically review and optimize database indexes. Properly designed indexes can significantly speed up the retrieval process, especially for frequently queried columns. In summary, achieving optimal performance and scalability for the database-intensive application in a Kubernetes cluster involves a combination of database-level optimization, cache mechanisms, Kubernetes-specific strategies, and effective monitoring. By employing these strategies and leveraging the relevant tools, I can ensure that the database-intensive application runs effectively and scales seamlessly within the Kubernetes environment. Question number 6. Can you explain the concept of blue-green deployment? Compare it with canary deployments and highlight scenarios where each approach is most suitable. If asked that question, I'll say, a blue-green deployment is a software release strategy that involves maintaining two identical environments, blue representing the current production environment and green representing the updated version. The switch from the blue to the green is swift, making the updated version live instantly. In contrast, canary deployment releases the new version of the subset to a few users before the full deployment. A blue-green deployment offers seamless updates with minimal downtime, allowing for easy rollback if issues arise. It's best for critical systems where downtime is unacceptable. Canary deployments is suitable for testing new features or changes with a limited audience, ensuring a gradual validation before the full release happens. Question number 7. You're required to implement an efficient monitoring and alerting system for a distributed microservice application. Describe the components you include in your system and the metrics you monitor to ensure the application's health. If asked that question, I'll say, thank you for asking that question. To establish a comprehensive monitoring and alerting system for our distributed microservice application, I'll incorporate a few specific components and closely monitor critical metrics to ensure that the health of our application is great. Firstly, I'll set up Prometheus as a metrics collection and storage system. It's designed for dynamic environments like microservices and provides valuable insights into the application's performance. Alongside Prometheus, I'll deploy Grafana for visualization, allowing us to create dashboards that offers a good overview of the different metrics that is currently being monitored. Service discovery will be facilitated through Kubernetes native feature or by utilizing tools like Console. This ensures that monitoring systems can dynamically adapt to changes. In terms of the different metrics, I'll closely monitor CPU and memory utilization to identify resource bottlenecks. Tracking response time and request rates will provide insights into the application's performance, while monitoring error rates will also help identify issues affecting the user's experience. The latency metrics will help us maintain optimal response time as well. Question number 8. How do you handle rollbacks in your production deployment using Kubernetes? Explain the steps you take to quickly revert to the previously stable version while minimizing users' impact. If asked that question, I'll say, when faced with the need to roll back a production deployment in Kubernetes, I personally follow a structured approach to ensure a smooth and rapid transition back to the stable state, minimizing any disruption for the users. Firstly, I'll carefully assess the situation that prompted the rollback. If, for instance, performance degradation or unexpected errors were detected, understanding the root cause is essential for effective rollback strategies. Next, I'll proceed by updating the Kubernetes manifest file to reflect the configuration of the previously known stable version of the application. This includes specifying the desired deployment configurations, container images, environment variables, and any associated resources. Once the manifest has been adjusted, I'll initiate the rollback process by employing the kubectl apply command with the updated manifest. This approach leverages Kubernetes' declarative nature, ensuring that the desired state is achieved while maintaining consistency across the cluster. For instance, let's consider a scenario where the new version of a microservice led to increased response time. To minimize user impact, I'll prepare the previous version configuration, including the appropriate image tags and resource limits. After applying the manifest, Kubernetes will orchestrate the rollback by scaling down the new version and scaling up the previous version. allowing the users to experience the stable performance they were accustomed to. Question number 9. Describe a scenario where you encountered a critical incident in the production environment. Walk us through the steps you took to diagnose this issue and how you coordinated with the team and implemented a resolution. Certainly, in my past role, I encountered a critical incident in the production environment that required a swift and methodical action to resolve it. The incident involved a sudden spike in the response time and an intermittent 500 error affecting the mission-critical microservice. Upon detecting the issue, my immediate focus was to diagnose the root cause. I promptly accessed our monitoring tool and analyzed metrics such as CPU usage, memory consumption, and network traffic. This data indicated a surge in incoming traffic, leading to resource exhaustion. Digging deeper into the logs, I identified a recurring pattern of requests that led to the database timeout. I initiated communication with a cross-functional team, including the developers and the database administrators, to collaboratively address the issue. We held a quick focus meeting within which, based on the urgency of the issue, we decided to implement a two-phase approach. First, mitigate the immediate impact, and then perform a thorough investigation later. We swiftly scaled up our microservices replicas to distribute incoming requests more evenly. Simultaneously, we tuned our database connections and optimized queries to alleviate the database bottlenecks. This immediate response led to a noticeable improvement in the response time, temporarily stabilizing the situation. For the long-term resolution, we initiated an incident retrospective. Each team member shared their observation, and we meticulously analyzed the log to pinpoint the origin of the request surge. Our investigation revealed a recent code change that introduced an inefficient database query, causing cascading timeouts. Question number 10. Discuss the role of infrastructure provisioning tools like Terraform in a cloud-native environment. How do these tools contribute to the dynamic and scalable nature of modern infrastructures today? If asked that question, I'll say, certainly. In a cloud-native environment, infrastructure provisioning tools like Terraform play a pivotal role in achieving the dynamic and scalable nature essential for modern infrastructure today. These tools provide a declarative way to define and manage infrastructure as a code, allowing the team to automate the provisioning and management of these resources. With Terraform, I can define the desired state of the infrastructure using configuration files. This includes specifying resources such as virtual machines, networking components, databases, and more. When I apply these configurations, Terraform interacts with the cloud provider's APIs to create, modify, or delete these resources as needed. The benefits of Terraform are significant. Firstly, it ensures consistency across the environment. Whether it's the development, test, or production environment, I can use the same configuration to create identical infrastructure setups, minimizing the risks of configuration drifts as well. Secondly, Terraform enables versioning and collaboration. Configuration files can be stored in version control systems, allowing for easy tracking of changes and collaboration among team members. This also gives us the ability to roll back to previous configurations if needed. Moreover, infrastructure provisioning tools contribute to automation. I can define complex setups with just a few lines of code, reducing the manual efforts required to set up the whole infrastructure. This not only speeds up the deployment process, but also minimizes the chance of human error. For scalability, Terraform excels in its ability to create and manage resources in parallel. This is particularly important for cloud-native environments where resources need to scale up and down rapidly based on the demand. Terraform state management also ensures that the actual infrastructure matches the defined configuration. It tracks the state of the resource, allowing me to detect drifts and make necessary corrections to maintain the desired state. In conclusion, infrastructure provisioning tools like Terraform empowers cloud-native environments by providing automation, consistency, versioning, scalability, and a dynamic resource management. This aligns perfectly with the requirements of modern infrastructure, allowing the organizations to build and manage complex, scalable, and reliable systems efficiently. Question number 11. Explain the concept of GitOps and how it streamlines the process of managing deployments and configurations in Kubernetes clusters. Provide examples of tools that facilitate GitOps practices. Certainly, GitOps is a modern approach of managing deployments and configurations in a Kubernetes cluster. It builds around the idea of using Git repositories as the source of truth for both the application code and infrastructure configuration. This approach promotes declarative configurations and automation, making it easier to maintain and manage Kubernetes environments. In a GitOps workflow, All configurations, including the application code, infrastructure setting, and deployment specifications, are stored in the Git repository. Any changes to the cluster state are made by updating the repository itself. This means that instead of making changes directly to the cluster, you make the changes on the repository and then use an automated process to sync those changes to the cluster. This has several advantages. Firstly, it enhances version control. Every change made is tracked in Git, allowing for easy rollback to the previous state and improved collaboration among the team members. Secondly, it provides consistency. The actual cluster state always matches the configuration in the Git repository, reducing the chances of configuration drifts and discrepancies between the environments. Thirdly, GitOps enables automation deployments and rollback. In essence, GitOps simplifies the management of Kubernetes deployments and configurations by using Git as the single source of truth. It promotes automation, version control, consistency, and a seamless rollback, leading to more reliable and efficient operations in the Kubernetes environment. Question number 12. You're tasked with improving the fault tolerance of an application that spans multiple cloud providers. How would you design a multi-cloud strategy to ensure high availability and resilience? If asked that question, I'll say, designing a multi-cloud strategy for high availability and resilience involves careful planning to ensure fault tolerance across multiple cloud providers. To achieve this, I'll approach the design with a focus of distributing the application's components and resources across different cloud providers, regions, and availability zones. This distribution will help mitigate the risk of a single point of failure should in case one cloud provider goes down. To facilitate easy traffic distribution and efficient failover, I'll implement global load balancing using a content delivery network. This will allow traffic to be routed to the nearest availability zone or any healthy cloud region, minimizing latency and improving overall application performance. For data resilience, I'll opt for multi-cloud data replication. By deploying databases and storage solutions across different clouds, I'll ensure data availability even if one cloud provider experiences an issue. Regular data synchronization and replication mechanisms will be set in place to maintain consistency. To manage the complexities of multi-cloud deployments and configurations, I'll employ infrastructure as a code tools like Terraform or CloudFormation. These tools enable consistent provisioning of resources across different cloud environments, ensuring that the infrastructure aligns with the desired state. Additionally, continuous monitoring and automated scaling plays a crucial role in maintaining high availability as well. In summary, a well-designed multi-cloud strategy involves distributing components, implementing global load balancing, ensuring data replication, using infrastructure as a code tools, and enabling automated monitoring and scaling. This comprehensive approach would enhance the application's resilience, minimize downtime, and provide a robust user experience across diverse cloud environments. Question number 13. Describe the use cases and benefits of serverless computing in a DevOps context. How does serverless architecture contribute to scalability, cost efficiency, and fast time to market? If asked that question, I'll say, certainly. In a DevOps context, serverless computing offers distinct advantages and use cases that aligns well with modern development and deployment practices. Serverless architecture, also known as function as a service, is particularly beneficial for certain scenarios. One primary use case is event-driven applications. Serverless computing excels when processing events or triggers, such as real-time data streaming, users' interactions, or IoT sensor data as well. Functions are executed in response to the events, allowing for efficient scaling without the need of managing infrastructure. Serverless architecture contributes to scalability by automatically provisioning resources based on demand. Functions are invoked only when needed, and the cloud provider handles the scaling behind the scene. Cost efficiency is another key benefit. With serverless computing, you're billed based on the actual execution time and the resources consumed by each function invoked. This granularity in billing allows cost savings since you're not paying for idle resources. Faster time to market is facilitated by the serverless architecture's inherent simplicity. Developers can focus on writing code for specific functions without worrying about the underlying infrastructure or deployment intricacies. In conclusion, serverless computing in DevOps context offers benefits such as event-driven scalability, cost efficiency through granularity billing, and faster deployment cycles by abstracting away from infrastructure management. Serverless architecture allows teams to concentrate on building functionality and delivering values to the customer. Question number 14. Share your approach in automating the deployment of application updates without causing downtime or service disruption. What deployment strategies and tools would you use to achieve this goal? If asked that question, I'll say, certainly. Automating the deployment of application updates without causing downtime is a critical aspect of ensuring a seamless service delivery. My approach to achieve this involves employing a combination of deployment strategies and tools as well. Firstly, I'll implement a blue-green deployment strategy. This entails maintaining two identical environments as I mentioned before. Secondly, I'll utilize a container orchestration platform, particularly Kubernetes. Kubernetes provides capabilities like rolling updates and traffic shifting through services. By defining appropriate update policies, I can control the pace of deployment and automatically manage traffic redirection, ensuring gradual and controlled updates. For tooling, I'll leverage CI/CD pipelines. Tools like Jenkins, GitLab CI/CD, or Circle CI allows me to automate the entire deployment process. These pipelines can be configured to trigger deployments when changes are pushed to the repository, running tests, building artifacts, and orchestrating the deployment process, all while ensuring the application remains available. Furthermore, I'll also employ infrastructure as a code tools like Terraform to manage the underlying infrastructure. And finally, question number 15. Discuss the importance of version control in DevOps practices. How does version control enhance collaboration among team members and contributes to the overall software development lifecycle? If asked that question, I'll say, version control is a cornerstone of DevOps practices that plays a pivotal role in enhancing collaboration, ensuring reproducibility, and contributing to the entire software development lifecycle. Version control systems such as Git provide a structured way to track changes to source codes, configuration files, and other project assets over time. This fosters collaboration among team members by allowing multiple individuals to work on different aspects of the project simultaneously. Reproducibility is another critical aspect where version control shines. Every change made to the code base is recorded, including who made the changes and when. This audit trail ensures that the previous state of the code can easily be revisited and reproduced even years later. Moreover, version control is integral to the software development lifecycle. It enables a seamless management of the different development stages, from initiating the development to testing, deploying, and maintaining the code. By tagging releases, creating branches for the specific features, and merging changes systematically, version control ensures that the software development process remains organized and manageable. Incorporating version control also aligns well with continuous integration and continuous deployment practices. Automated builds and deployment pipelines can be triggered based on the code changes, and the version control artifacts enable consistency and reliable deployments across different environments. In conclusion, version control is paramount in DevOps practices due to its capacity to enhance collaboration, maintain reproducibility, and contribute to the various stages of the software development lifecycle. It's an essential foundation that empowers the teams to work efficiently and deliver reliable software, and also embrace a culture of continuous improvement. If you watched this video to the end, I would love to say congratulations to you. You're 90% more prepared than other candidates out there. But if you have any burning questions about specific technical interview scenarios or concepts, drop your queries in the comment below. My team and I will create another video to address your questions directly. After all, this series is about empowering you with the knowledge you need. Now, all you need to do is put in the work, and I guarantee you, you're more than ready for your upcoming interview. Remember, this isn't about just answering the questions. It's about showcasing your skills, your approach, and your adaptability as a DevOps engineer. So stay grinding, stay hustling, and I'll see you on the next one. Cheers!